Right? So let's get to chemical equations. Right? So this is like the real meat of what people think of as being chemistry most of the time. I've got some sort of chemical reaction. I am changing matter of one type into matter of another type through the magic of energy and bond formation and bond breaking. It involves the reorganization of atoms in one or more substances. In our chemical equation, we're going to put our reactants on the left-hand side of an arrow, and the products, that's the things we make, located on the right-hand side. So here we've got methane combining with oxygen to form carbon dioxide and water as products. So this is our standard combustion reaction, right? So this could be your go-to combustion reaction. If somebody says, what's a combustion reaction? You CH4O2 plus O2 gives you CO2 and H2O, right? Some bonds are broken and new bonds are formed. That is what makes it a chemical reaction and not just a physical change, right? You're ending up with new materials on the right-hand side that are different from your materials on the left-hand side, right? Both sides are still going to have the same number of atoms, but they're arranged in different ways and they're held together with different bonds. So atoms are not going to be created or destroyed. That's our conservation of matter. Right? The number of atoms on the left are going to equal the number of atoms on the right. Right? The number of atoms are the same on both sides. I've got one carbon over here, one carbon over here. I've got 1, 2, 3, 4 oxygens over here. I got 1, 2, 3, 4 oxygens over here. I got 1, 2, 3, 4 hydrogens. I got 1, 2, 3, 4 hydrogens. All right, so if I need to make this reaction between methane and oxygen, I'm going to need 2 times as many oxygens as I've got methanes, and I'm going to produce 1 carbon dioxide in this reaction cycle and 2 H2Os in order to make sure that mass balance works out properly. So, the meaning of a chemical equation. It contains information on the nature of the reactants and the products and the relative numbers of each. They're also going to provide the physical state of the reactants and products. That is going to be super important when we start talking about thermochemistry or electrochemistry, because that state matters, right? Especially in the next course when we're going to talk about everything being energy, right? The energy being the primary component. It takes a lot more energy for something to be in the gas phase than it does to be in the solid phase. Versus it, and the liquid phase is going to take an intermediate amount of energy. We've got 3 main symbols that we're going to use. If something is a solid, we're going to give it a symbol S. If something is a liquid, we'll give it a symbol L. If something is a gas, we'll give it a symbol G. And if something is an aqueous solution, we will give it the symbol AQ for aqueous. Or sometimes we will leave that out altogether because there are so many reactions that happen in aqueous solution that sometimes we'll just leave it out. Like if you've got something like Na, sodium plus AQ in aqueous solution, and, well, not sodium. How about silver, Ag plus, right? AQ, and chlorine minus. They're going to form AgCl, which is a solid, right? So these guys are going to be aqueous solution, but because so much stuff happens in aqueous solution, and because it's got this whole extra letter going on here, right? Sometimes we will drop the AQ part. So if you do not have anything on there, right, you just have an ion floating around, it is generally going to be assumed that you're talking about an aqueous solution. If you have something like C6H10O2, right, and you don't put anything in there, my assumption will be that it is AQ, a solution. Right? So for me, if you leave off at AQ, I will assume it is an AQ. If it's got nothing in there indicating state, I'm going to assume aqueous solution. Right? That may not be true for other people you work with going forward. Right? So our balanced chemical equation, right, our BCE, all right, you will hear me talk about the BCE at length. The balanced chemical equation is often step 0 for doing a lot of other stuff. So knowing how to balance a chemical equation is super important. Our balanced chemical equation is the key to stoichiometry. Stoichiometry is all about working within a balanced chemical equation and then seeing how do things relate to each other based on this balanced chemical equation, right? And this balanced chemical equation is really just restating the law of conservation of matter, right? So it's not a big surprise, right? You know, like matter is conserved. You look at Dalton's law that says, hey, when I form new compounds, they're going to be formed in new predictable ways. It's taking those two very simple laws and saying, we're going to give it a new name, stoichiometry, we're going to count stuff, right? So when we do this, we need to make sure that it is balanced in terms of the masses on each side and the number and types of atoms on each side. So if I've got CH4 and O2, I'm going to need two O2s in here in order to balance everything out properly, because I form H2O as a product and CO2 as a product. And I got to make sure I've got the right number of oxygens. 2 times 2 is 4. And here I got 2 plus 1 times 2 is 4. I got to make sure I've got the same number and type of atoms on each side. Now, like I said, these guys are really important. Right? It represents all atoms present in the reactants have to be accounted for in the product. An unbalanced chemical equation is not useful, but it is of limited utility. When balancing chemical equations, care must be taken to avoid altering the chemical formulas or compounds. So you can't change it and write new stuff. That's not part of the product. So you can't change what your reactants are. You can't change the subscripts, and the atoms cannot be altered or added to or subtracted. You can't swap out an Ag with a H plus just because it makes your life easier. Right? Now, when it comes to balancing chemical equations, there are two approaches. Right? This is the one your book uses, and it is almost the opposite of the approach that I use. So they're going to start with the most complicated molecules. Me, I'm going to start with the least complicated molecules. I see something out there like this oxygen, I'm going to go for that oxygen first. Your book is going to show you how to go for the complicated ones first. Right? I think it is harder to learn the book method, so I'm going to show you the book method here, and if you want to, I can do some practice ones with you guys where we look at the simpler compounds first. All right, so let's look at the following unbalanced equation. We got C2H5OH, right? That's our ethanol liquid, and we're going to combine that with oxygen. All right, so let's say you wanted to make a flaming moe. You're also going to produce a lot of heat in this reaction, right? So you're going to do plus heat. Right? It's an exothermic reaction. You're going to see some fire happening. One of my stupid human tricks is that in college I joined the Street Performers Club, and I could not juggle to save my life, but I was really good at playing with fire. And so I learned how to breathe fire and like make spit one of those big fireballs. That is not compatible with having a beard, kids. So do not try to drink a flaming shot if you have a beard or a mustache, because you will soon not. Okay? So in here, their most complicated molecule is this ethanol. So you're going to look at the elements within that complicated molecule. So you've got 2 carbon atoms on the left, and you got 2 carbon atoms over here on the right. So your carbon left to right is going to be balanced. Then you're going to look at the hydrogen atoms, right? Here I've got 5 plus 1, that's 6 on the left. And over here, right, I've got 3 times 2, that's 6 on the right. If I look at the oxygen atoms, I've got 1, and then 3 times 2, and that's going to give us a total of 7 oxygens on the left. And here I've got 2 times 2 is 4, and over here 3 times 1 is 3, with 7 oxygen atoms on the right. So our number of oxygen atoms balances, our number of hydrogen atoms balances, and our number of carbon atoms balances. So that's how we're going to verify our results. You check them up at the end. Right? So let's write the unbalanced chemical equation using the correct chemical formulas for this process. So I've got H2 gas, hydrogen gas, and oxygen gas combining to form liquid water. And probably form hydrogen or H2O gas, right? So if I look at my hydrogens, I've got a hydrogen, neither of them are particularly simple or complex. But over here I've got two hydrogens, and over here I got two hydrogens. So at the start you're like, oh, hydrogens are good. But let's look at our oxygens, right? How many oxygens do I have over here? I got two oxygens over here, and over here I've only got one oxygen. So in order to balance our oxygens out, we're going to put a 2 in front of our H2Os. Well, when I do that, I'm going to double check my hydrogens. Well, now here I've got 2 times 2 hydrogens, that's 4 hydrogens. And that's not going to work. So I've got to go back over to here, right, and double these guys up. And now I've got 2 times 2 is 4. Now my hydrogens are happy, and my oxygens are happy, and my H2Os are happy. Right, so there's a lot of iteration, a lot of backing and forthing, right? Over to here. Well, now I got this guy balanced. Well, and I got to fix this guy. Well, I fix this guy. Now change something over here. Well, now I got to fix this guy over here. So yes, this can be a long and tedious process, right? But it is definitely doable. And I, as a student, did not like doing this process. It is not something that I am good at. Okay? If it is necessary, right, so if necessary, you can reduce the coefficients to their smallest whole number values by dividing them all by a common divisor. We kind of want those things to show up as a small whole number ratio, so that whatever your smallest guy has a coefficient of 1. But this, all right, you can work with that. Right? That is a balanced chemical equation. It's just not the most elegant version, right? So you want to give me the pretty one, right? The other one that would work too is you could do, right? You could do H2 plus half an O2 is going to give you H2O, right? So if you saw this initial H2 and O2 giving you H2O, and you're like, well, I got 2 oxygens over here and 1 oxygen, all I got to do is cut this guy in half, right? Well, then you can multiply each of these guys by 2. This one over here is also workable. The reason why we want to do this as small whole number ratios is that it will then reflect what happens on both your molecular scale. Right? So you can't, on the molecular individual molecule scale, have half an oxygen. Right? It doesn't work. You can't have half an oxygen. But if you're talking about a mole's worth of oxygen, right? If I'm 6.02 times 10 to the 23rd oxygens, and I cut that in half, and I got 1 or 2 leftover oxygen molecules, it's not going to matter. So if you're working on the mole scale, this is going to be perfectly valid, right, to work with. Like 1 mole of hydrogen, half a mole of oxygen gas gives me 1 mole of water. That's perfectly workable. But do it pretty and do it right. Once you've got this guy, lowest common multiple this, here I got a 2, multiply everything by 2, get into the coefficients that are smallest, where 1 is going to be your smallest. You check your answer by making sure that the numbers and kinds of each atom on both sides are the same on each side of the equation. Right? So let's do a couple of examples here. I'm just kind of taking a look at this first guy. I'm going to see I've got a boron over here. So I'm looking for my non-hydrogen, non-oxygen, non-carbon guys kind of first. Right, so I'm looking at this boron over here. I see 1 boron on the left. I see 1 boron on the right. Right now they're happy. Now I want to look at these chlorines. I've got 3 chlorines over here and 1 chlorine over here. So my first guess is I'm going to put in 3 chlorines over here. When I do that, now I've got 3 chlorines and I've got 3 hydrogens over here. How many hydrogens on each side do I have? So now I've unbalanced the hydrogen. My back and forth is once I make a change in one thing, I'm going to go back to the other side and make sure it all works out. So I got 3 hydrogens, 3 coming from the HCl, I've got 3 coming from over here. So I've got right now 6 hydrogens on the right. How many hydrogens do I have on the left? Well, nothing over here, 2 over here, so I'm going to multiply this dude by 3. So now I've got 6 hydrogens on each side. And you can, just kind of keep track. I got 1 boron on each side. I got 6 hydrogens on each side. In terms of chlorine, I've got 3 chlorines on the left, and I got 3 chlorines on the right. So now I've got my hydrogen done. Now let's take a look at the oxygen. Here I've got 3 oxygens in here, and I got 3 oxygens in here. That's all I need to do. My oxygens are now balanced out at 3 apiece. If you've got a polyatomic ion group, treat them as a group, right? This SO4 minus is a polyatomic ion. It's not going to break itself up, so you can treat these guys as a chunk. So here we've got H2SO4, and then here we've got aluminum SO4, and then we've got 3, right? So this guy's got 3 around it. So we're going to treat these SO4s as a group. It's going to make our life a little bit easier. Now looking at our non-hydrogen, non-carbon, non-oxygen guys. I'm going to go for this aluminum, right? Here's aluminum just hanging out all by itself. I see aluminum over here. I got 1 Al over here. Over here I've got 2 aluminums, which means I want to come over here and do this aluminum over here, right? If I mess with this guy, it's not going to change anything else. So that's why I'm going to go for the easiest guys first. I look at my SO4s, right? I've got 1 SO4 over here, right? And only 1 over here, and I got 3 over here. And so first thing I'm going to do is I'm going to treat these SO4s as a group. I got 3 on the right, 1 on the left. I'm going to put a 3 in here, right? If I've got 3 in here, what I've done is I've unbalanced my hydrogen, right? I've got 6 hydrogens on the left. Right now I've only got 2 hydrogens on the right, so I'm going to take this guy, I'm going to multiply it by 3, and now I've got 6 hydrogens. Right? I'm going to double check, 2 aluminums, 2 aluminums. 6 hydrogens, 6 hydrogens. 3 SO4s, right? 3 times 1, 3 times 1, 3 SO4s. We're going to treat those guys as a group. Right? Looking at calcium siloxane. Silicate. Right. I've got calcium, silicon, and oxygen. I've got HF, I got SiF, I got calcium difluoride, and water. Right. I'm going to look for the things that show up in the least amount of places first. I like to go easy first. So looking at my calcium, got 1 calcium on the left, got 1 calcium on the right. Now I'm looking at my fluorines. I got 2 fluorines over here. Another 4 fluorines over here. I've got 6 fluorines on the right, which means I need to have at least 6 fluorines over here. When I've done that, now I've got 6 hydrogens. So I'm going to bump over here. I'm looking at my 6 hydrogens. I've got 6 hydrogens here. How many hydrogens do I have over here? I've got 2. So I'll change this guy to a 3. This guy now becomes 6. When I do that, now I've unbalanced the oxygen. I got to look and see how many oxygens do I have. Here I got 3 oxygens on the right. How many oxygens do I have on the left? I've got 3. I'm done. At least with the oxygens, right? But now I'm going back and I'm double checking, right? Okay, so I got 1 calcium, 1 calcium, 1 Si, 1 Si. I got 3 oxygens over here. I got 3 oxygens over here. I got 6 hydrogens over here. I got 3 times 2, 6 hydrogens over here. I got 6 fluorines over here. Oh, and I got 4 over here. Right? So what do I got to do now is look in between the silicon and the fluorine to make sure these guys work out. So what I'm going to do, right, is I'm just going to take everything and I'm going to start multiplying. If I need to. So I don't need to multiply anything in this guy, so I'll move on to the next example. So let's balance the equation representing the combustion of hexane. Now these straight chain alkanes, so it's going to be like C6, H14, or C5, and the appropriate number of hydrogens. They're all going to follow a nice pattern to them, so you can kind of figure out the pattern. So we're going to balance one for hexane. So hexane will be 1, 2, 3, 4, 5, 6, and it's going to have hydrogens all around it. Right? These little lines in here represent hydrogen stuck to a carbon, and each of the little points on here is going to represent a carbon. Right? This little juice carbon, there's a carbon, and there's a carbon, and it's got 3 hydrogens. So if I look at our C6H14, we're going to react that with oxygen. We're going to form carbon dioxide and H2O. So I've got carbon I've got to worry about, I got hydrogen I've got to worry about, and I got oxygen that I need to worry about. These guys are all kind of they're all kind of the trickier ones to work with because they show up in a lot of things. They show up in multiple places. So the first thing I'm going to do is carbon, because I only got carbon showing up in one place. I got hydrogen and oxygen showing up in both of these guys on the left. Carbon only shows up in the 2 places. I'm going to throw in a 6. That's going to balance out my carbon. All right. Then, to balance out the hydrogens, I've got 14 hydrogens on the left. I'm going to do 2 times 7, 14 on the right. Right? Now we've got 19 oxygens on the right, 12 plus 7. We're going to balance the oxygens out on the left by multiplying by 19.5. Totally legitimate move when you are balancing stuff out and you're working through this process. And if you're working on the mole scale. Wouldn't work out if you're working on the atomic scale. Can't have 19.5 oxygens. There's no such thing as half an oxygen. But if you've got 19.5 moles, sure, you can have 19.5 moles. Right? So now I've got this guy. I got 2 options, right? What I can do is I can either multiply or divide, right? I got some sort of obvious fraction that worked out well here, right? 19.5 molecules doesn't make sense. What I can do now is, if we're talking about moles, it's cool, but we want to get that down to the lowest possible common denominator. I'm going to multiply everything by 2. So we'll get 2 C6H14s and 2 times 19.5. And I'll have 39 oxygens, and that will go to 12 carbon dioxides and 14 H2Os, right? So all I did is I took this whole schmear and I said, okay, I want to get rid of this half on the bottom. I'm going to multiply by 2. Right? Balancing combustion reactions, like I said, follows a pattern. They're fairly straightforward to do. We're going to have some sort of reactant. It's going to be CXHY or CHYO on the left, and we're going to end up with carbon dioxide and water on the right. We will talk about different types of reactions. There's a couple of different types of reactions, like single displacement or double displacement or combustion or redox. Combustion is one of the main classes of reaction. So first, balance those carbons. They're only going to show up in the 2 spots, right, in our hydrocarbon, and then over here in our carbon dioxide. You know, hydrogen shows up in 2 places, oxygen shows up in 2 places, or hydrogen shows up in 1 place, oxygen shows up in 2. So do the carbon, then do the hydrogens, right? Then balance the O2s. Use halves and multiply all coefficients by 2 when you're done doing it, right? So if we've got our reaction on different levels, like we said, we can do this at the microscopic level and the macroscopic level, which really actually falls in line pretty well with some of the alchemical concepts that people were looking at with the microcosm versus the macrocosm, and how concepts and magic work with if you can make a change on the microcosm, you can affect things in the macrocosm. So if like you make the voodoo doll and you poke it in the elbow, and then somebody else is like on the macro scale, ow, my elbow hurts, right? There's correspondences between them. It doesn't quite work the way that our magical thinking predecessors conceived of it, but we do have both a macro scale and a micro scale. So we can look at this as 2 hydrogen atoms reacting with 1 oxygen molecule to give us 2 water molecules. Or we can think of it as the macroscopic view. 2 moles of hydrogen gas react with 1 mole of oxygen gas to yield 2 moles of liquid water. Right? One of these things is describing what's happening on a very, 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 very small scale, and the other is describing what happens on kind of a laboratory scale. Right? We can weigh 32 grams. Right? And it's really, really hard to get in and look at an individual water molecule or an individual hydrogen molecule. So let's look at our concepts. Which of the following is true about a balanced chemical reaction? Pause. Resume. Is it the number of molecules is conserved? The coefficients tell you how much of each substance you have. The atoms are neither created nor destroyed. The coefficients indicate the mass ratios of the substances used, or the sum of the coefficients on the reactant side equals the sum of the coefficients on the product side. And you should know that it's the atoms are neither created nor destroyed. The same number and same type of atoms on both the left hand and the right hand. The number of atoms in each type of my reactants are equal to the number of atoms of each type in my products. Now, the number of molecules may or may not be conserved, right? So you look at your water reaction, right? I got 3 on the left and 2 on the right, so that's not true. Right? The coefficients tell you how much of each substance you have. Well, if I take hydrogen gas in a balloon and I explode it into an atmosphere, I've got a lot more oxygen than I do hydrogen. I'm going to end up with leftover oxygen. So it's not going to tell you how much you have. It's going to tell you how they combine. Right? So this one's a little tricky, but it's an X. The coefficients indicate the mass ratios of the substances used. Yeah, if you account for the atomic masses. Right? So I've got 2 hydrogen molecules, but those 2 hydrogen molecules are going to account for like 4 atomic mass units. My 2 oxygens over here are going to be 32 atomic mass units, right? So my mass ratios are not directly correlated to the coefficients, right? You got to account for the atomic masses. The sum of the coefficients on the reactant side equals the sum of the coefficients on the product side. That's just the same thing as number 1, but in fancier words. All right, so let's look at balancing a chemical equation example again. Chromium compounds exhibit a variety of bright colors. That's where we got the word chromium for color. Right? Compounds exist in a variety of colors. When solid ammonium dichromate NH4 2Cr2O7, a vivid orange compound, is ignited, a spectacular reaction occurs. It is a pretty cool reaction. So another Dr. Stewart story here is I went to kind of a hippie kindergarten, which meant that we did some things that were really cool and some things that were very hippie, and the janitor had long hair and we called him Ms. Ted because it was still the 70s and it was rural Pennsylvania. And so, but on the other hand, they also did some really cool stuff. And so they did this ammonium dichromate experiment where you've got the dichromate in there and you set it on fire, and they did this as a volcano, and it gives you this very dramatic volcano type of reaction. So, they had the paper mache volcano and they filled it with some dichromate and they set it on fire, and it was like really fiery, and here's a little YouTube link to that. And so when I moved out of the hippie kindergarten into first grade, and they were like, okay, class, we're going to do the volcano experiment, and they got out like some food coloring and some baking soda and some vinegar, I was like so disappointed because I was expecting there to be like fire and stuff going on, and it was like, that just looks goopy and messy. Like this is not what I was used to. You're making me sad here. There's not enough fire. And that's why we all got into chemistry, because we like playing with fire and we get to do it a lot. Okay? So we're going to assume that there's a reaction that's going to have N2 molecules and water vapor. So the products are going to be nitrogen gas and water vapor and solid chromium 3 oxide. And we got a formula for chromium dioxide by recognizing that the Roman numeral 3, you realize it means that it's a chromium 3 plus ions. So for our neutral compound, we're going to have chromic oxide, which is Cr2O3. Right, so our unbalanced equation is we've got NH4 ammonium, and then we got our chromate Cr2O7, and we're going to form our Cr2O3, our chromic oxide, and we're going to form nitrogen gas and water gas and a lot of heat. Note that the nitrogen and chromium are balanced, right? So our nitrogen and our chromium are already starting out nice and balanced. Two chromiums, 1 times 2 and 2, right? But our hydrogen and our oxygen are not, so we're just going to use a coefficient of 4 to balance out those hydrogen atoms. So we end up with NH42, Cr2O7 gives us Cr2O3 solid, N2 gas, and 4 H2O. So we balance out our oxygens and our hydrogens.